The deep ocean is no longer unreachable. New machines don't just survive underwater. They think, adapt, mimic life, and work like tiny explorers in a world darker and stranger than space itself. These technologies are revolutionizing how humans see, map, and interact with the deep sea. And they are only getting smarter. Next generation deep sea technology. Deep sea exploration is evolving beyond large tethered robots and steel submersibles. The current frontier focuses on autonomy, intelligence, and innovative mobility that allow machines to perform complex tasks in extreme underwater environments without constant human control. This shift is powered by advancements in artificial intelligence, soft robotics, autonomous navigation, and new sensor networks that work in concert to transform how the deep ocean is explored and monitored. AI-powered autonomous underwater systems. One of the most transformative trends in ocean exploration is the integration of artificial intelligence with autonomous underwater vehicles, AUVs. These systems can detect, classify, and report underwater objects using onboard neural networks and machine vision, essentially learning from what they see. For example, a recently developed AI-powered AUV system uses real-time object detection, deep learning, and large language model summaries to analyze marine environments without humans at the surface. This technology reduces risk, accelerates discovery, and opens vast areas of the seafloor to scientific research that would otherwise be too dangerous or expensive to explore. Soft robots, inspired by marine life. Traditional submersibles are rigid and bulky. A new generation of soft robots takes inspiration from sea creatures themselves. These machines replicate the flexibility and adaptability of deep-sea organisms, allowing them to maneuver through complex terrain, withstand pressure without heavy protective hulls, and minimize disturbance to fragile environments. Innovations include jellyfish-like robots that glide silently and conserve energy, which could be used for ecological monitoring, environmental mapping, or even covert surveillance missions. Ultra-deepwater autonomous vehicles. Expanded. Ultra-deepwater autonomous underwater vehicles are designed to operate in the HODL zone, typically defined as depths below 6,000 meters and extending to nearly 11,000 meters in the deepest ocean trenches. At these depths, ambient pressure exceeds 80 megapascals and can reach more than 110 megapascals near the trench floor. This environment places extreme mechanical, electrical, and operational demands on vehicle design. To survive these pressures, ultra-deep AUVs rely on pressure-tolerant architectures rather than traditional lightweight housings. Critical electronics are enclosed within thick-walled titanium or high-strength steel pressure vessels, often spherical or short cylindrical in shape to minimize stress concentrations. Non-critical components such as batteries and some sensors may be oil-filled and pressure-compensated, allowing external pressure to equalize without structural failure. Buoyancy is achieved using syntactic foam engineered specifically for HODL depths. Unlike standard deep-sea foam, HODL-rated syntactic materials use microspheres with higher compressive strength and carefully controlled size distribution to prevent collapse under extreme pressure. Even small buoyancy losses at these depths can compromise vehicle trim and mission endurance. Navigation presents a major challenge because GPS signals cannot penetrate seawater. Ultra-deep AUVs combine inertial navigation systems, Doppler velocity logs, depth sensors, and acoustic transponders deployed from the surface or seabed. Over long missions, navigation drift accumulates, so vehicles periodically recalibrate using terrain relative navigation by comparing real-time sonar data with pre-existing bathymetric maps of the trench floor. Sensor payloads on ultra-deep vehicles are optimized for high-resolution seafloor mapping and scientific measurement. Multi-beam echo sounders generate detailed bathymetry even in steep trench walls, while side-scan sonar reveals fine-scale texture and geological features. Additional sensors may include magnetometers, chemical analyzers, temperature probes, and turbidity sensors to study tectonic activity, sediment transport, and deep ocean chemistry. Power systems are another limiting factor. Because ultra-deep AUVs operate untethered, they rely on high-energy density battery packs, often lithium-ion or silver-zinc, housed within pressure vessels. Energy budgets are tightly managed, with mission planning software balancing speed, sensor usage, and navigation accuracy to maximize coverage while ensuring safe recovery. Communication during missions is limited to low-bandwidth acoustic links, used primarily for status updates and emergency commands. Full data sets, including sonar maps and scientific measurements, are stored on board and recovered only after the vehicle resurfaces. This delayed data model makes system reliability critical, as real-time intervention is not possible at extreme depths. Ultra-deepwater autonomous vehicles are essential for exploring ocean trenches that are otherwise unreachable by humans or tethered systems. They enable repeated long-duration surveys without the cost and risk of crewed submersibles. As materials, science, energy storage, and onboard intelligence continue to improve, these vehicles are expected to play a central role in mapping Earth's least understood regions and studying processes that influence earthquakes, plate tectonics, and deep ocean ecosystems. New mapping and simulation technologies. Exploration goes beyond robotics. It now includes digital technologies like marine digital twins. These are virtual simulations of the ocean environment built from real-world data. By fusing multiple data sources, bathymetry, currents, sensor networks, and real-time measurements, digital twins help researchers predict ocean behavior, plan missions, and improve safety. This innovation supports everything from autonomous navigation to offshore infrastructure planning. Intelligent observation networks. Rather than single vehicles, scientists are building networks of sensors and platforms that continuously monitor deep-sea conditions. These can include clusters of autonomous devices that share temperature, pressure, chemical, and biological data in real time. When coupled with AI, these networks can alert researchers to seismic events, ecosystem changes, or underwater volcanic activity, essentially creating a global nervous system for the oceans. The next frontier. The future of deep-sea technology is increasingly intelligent, adaptive, and interconnected. As systems gain greater autonomy, machines are no longer limited to executing pre-programmed tasks, but are beginning to interpret their environment, adjust mission behavior, and respond to unexpected conditions in real time. This shift reduces reliance on surface control and allows exploration in regions where communication is minimal or non-existent. Advances in materials, science, energy storage, and pressure-tolerant electronics are extending mission duration and operational depth. Vehicles can now remain submerged longer, travel farther, and operate more reliably in environments once considered inaccessible. At the same time, bio-inspired designs are enabling quieter movement and reduced disturbance of fragile deep-sea ecosystems. Deep-sea technology is also becoming more collaborative. Networks of autonomous vehicles, seabed sensors, and surface platforms are being designed to operate as integrated systems rather than isolated tools. Together, they can monitor geological activity, map vast areas of the seafloor, and detect changes in ocean chemistry and biology over long time scales. As these technologies mature, they will continue to expand humanity's understanding of the deep ocean, a region that influences climate, tectonic processes, and global ecosystems. Much of the ocean floor remains unexplored, and each advancement brings new opportunities to observe, measure, and understand a world that has remained hidden for most of human history. The deep ocean is no longer defined solely by its inaccessibility. It is becoming a frontier shaped by engineering, intelligence, and long-term observation, where machines extend human presence into the most extreme environment on Earth.